Centuries ago, the famous sword makers of Toledo discovered that the hand-forged blades for the Spanish conquistadors lasted much longer if they continued to hammer them after the metal was cold. In the late 1920s, researchers at the General Motors Tech Center discovered that valve springs for the Buick and Cadillac engines lasted much longer if they hammered them with millions of tiny pieces of round steel shot. The secret? If a metal is hammered sufficiently to indent the surface, even microscopically, a residual compressive stress is induced in the surface. When a metal bar is flexed a sufficient number of times, it will eventually start to crack from metal fatigue on the side where the metal is being stretched in tension. A crack will not occur on the opposite side that is being pushed together in compression. So that if we could somehow induce a compressive stress on both surfaces, the metal bar would last much longer without cracking or even never fail. Shot peening by bombarding the surface with millions of tiny spheres is a practical way to introduce a residual compressive stress in the surface. Now, when a flexing load is applied, it must overcome the compressive stress from the shot peening before a crack can start. This often means that the life of the part has been increased by orders of magnitude. Metal fatigue cracks can only start where the metal is in tension, never where the metal is in compression. The use of controlled shot peening is a refinement of the process used by the researchers at General Motors, itself an evolution of the hammering by the sword makers of Toledo. Metal Improvement Company began operations in Los Angeles in 1946 to service the aircraft manufacturing industry in Southern California. One of the original founders was Professor Henry Fuchs, who started his career at the research laboratories of General Motors. MIC offered controlled shot peening services and manufactured its Peenematic line of shot peening equipment from this facility. In the early 1950s, working with Lockheed Aircraft Corporation, Metal Improvement Company developed peen forming to produce the aerodynamic curvatures of the wing skins for an aircraft called the Super Constellation. Today, MIC continues to peen form wing skins for the big three builders of commercial airliners, as well as for a number of military, commuter, and business aircraft. In 1968, Metal Improvement Company became a wholly owned subsidiary of the Curtiss-Wright Corporation. Today, Metal Improvement Company provides controlled shot peening services for over 5,000 customers located in the major industrial centers throughout North America and Europe. In addition, MIC offers PeenTex, a non-directional texturing much favored by architects. MIC provides commercial heat treating of metal parts and also is a leading supplier of ultra-precision reed and ring valves used in two-cycle engines and in the compressors for refrigerators and air conditioners. Our valves are also used in air compressors and vacuum pumps. Returning to the subject of metal fatigue, many common manufacturing processes actually have a negative effect upon fatigue because they can introduce residual stresses in tension or because they can leave tool marks that become stress concentrations where cracks are likely to initiate. On the beneficial side, surface hardening will produce low compressive stresses. Smoothing the surface by honing or polishing removes the tool marks and distributes the applied stresses, but can be expensive. Rolling certainly induces very high residual compressive stresses, but is limited to cylindrical geometry. Controlled shot peening has no such limitation and is generally the most economical. This chart shows two SN curves used by engineers to plot the effects of metal fatigue. The S stands for stress, increasing up the vertical axis, and N stands for number of cycles. The curve represents the likely fatigue failure points for given conditions. Suppose that a particular part is operating at a stress level of 80,000 pounds per square inch. Without controlled shot peening, the part will probably fail at about 1,000,000 cycles. However, with shot peening, we have raised the endurance limit above our operating stress level, and, at least in theory, the part will never fail in fatigue. On the other hand, suppose 1,000,000 cycles is okay, but we would like to use a greater load. These curves show that we can go up to 110,000 psi and still get 1,000,000 cycles if we shot peen the part. What's a good example? The gears that are in your car's transmission. In all likelihood, the transmission was originally designed for a less powerful engine than your car has now. How do the gears and shafts survive? They are shot peened prior to assembly. To overcome metal fatigue, many parts can benefit from controlled shot peening. Springs of all sorts, gears of all sizes, crankshafts and connecting rods, turbines, rock drills, mining equipment, snowmobiles. In short, if it's under high stress, shot peening will make it last longer. Or maybe you can borrow an idea from the aircraft industry. Design a lighter part and use shot peening to make it stronger. There are many stress-related modes of failure that controlled shot peening can correct. But another important one is a condition known as stress corrosion cracking, or SCC. SCC is a progressive fracture mechanism in metals that is caused by the simultaneous interaction of a corrodant and a sustained residual or applied tensile stress. Structural failure due to SCC is often sudden and unpredictable, occurring after as little as a few hours of exposure, or after months or even years of satisfactory service. Virtually all alloys are susceptible to SCC by a specific corrodant under a specific set of conditions. Often, the corrodant will be considered very mild in terms of general corrosion, but will cause severe cracking where tensile stresses are present, such as in the heat-affected zone of a weld or in a highly stressed fastener. The obvious solution to stress corrosion cracking is to change the nature of the surface stress from tension to compression, since, as in fatigue, SCC cannot occur in any metal under compression. Controlled shot peening becomes the method of choice by which to generate the residual compression. And because this residual compression is close to equaling the yield strength of the metal, stress corrosion cracking is virtually eliminated as a potential cause of catastrophic failure. Metal Improvement Company has deployed its technicians into the field with portable equipment to more than 30 countries to shot peen structures that are too large to transport. Not surprisingly, most of these big structures are shot peened against SCC, usually in the weld areas. Controlled shot peening is recognized by NACE and ASME, among many other technical societies, and has been very effective in combating both fatigue and stress corrosion cracking in the heat-affected zones of welds. Some examples include an ammonia fertilizer storage tank, known as a bullet, a sulfuric acid reactor lined with pure zirconium, a pulp digester at a paper mill, a process heat exchanger. Not all SCC failures are weld-related. A carrier-based aircraft, the chlorides in common salt are a frequent cause of SCC. And a typical nuclear power station, where we peen the tubing in gigantic heat exchangers known in the industry as steam generators. MIC has peened over 300,000 tubes in nearly 100 steam generators, using specially designed robotic peening equipment that is controlled entirely by computers located outside the containment structures. The Inconel tubing is only 3/4 of an inch in diameter, and we peen the inside surfaces. Actually, we can peen holes less than 1/8 inch in diameter. You can be sure that there are many parts shot peened by MIC on the airplane that takes you to your next business meeting, on the car that you drive to get there, in the refrigerator that preserves your food, in the trucks that bring it to you, in the buses and trains, in the machines that build the roads and fasten the tracks. You'll find parts that are shot peened by Metal Improvement deep in the Earth's crust and at the bottom of the sea. You'll find MIC on the space shuttle, and even still on the surface of the moon. Metal Improvement Company is the largest company in the world that processes metal parts on a subcontract basis. MIC was the first to introduce computer-monitored and controlled shot peening equipment for flight-critical components. We introduced and licensed a process called Peen Scan that uses a fluorescent tracer to evaluate shot peening coverage. MIC has developed a unique process called search peening that enables us to positively identify and subsequently remove deep exfoliation corrosion on aircraft wing and tail surfaces that is much more effective than eddy current testing. Another innovation developed by MIC is called Peen Stress, a computer program that allows us to predict residual stress profiles for a variety of shot peening conditions for a whole library of metals. How about a method of evaluating the residual stress profile beneath the surface on an actual part without having to destroy the part as you have to today? Metal Improvement Company is funding both these development efforts. So what is MIC really all about? Perhaps our mission statement says it best. Metal Improvement Company Incorporated is an entrepreneurial company that strives to excel in the field of material enhancement for the metalworking industry. We will maintain our reputation for high-quality, low-cost service to our customers, and through our dedication and involvement in providing solutions to their needs, develop our relationship with them into one of true partnership. We are proud of our mission, but we want you, our customer, to remember that our primary objective is the prevention of metal failures. An in-depth technical seminar is available from Metal Improvement Company. Please contact your local MIC Technical Service Manager for an agenda.